Hello and welcome to the channel. In this video series, we are reviewing the principles and practices of commercial construction. This video is about the textbook's chapter 14, and that is all about building insulation. So in building construction, the use of insulation is an essential component in the design and construction of the building envelope and is important for the protection of structural members within the building frame. The need for appropriate fire protection of structural members within buildings has been vividly illustrated by recent world events. As wall systems have become more sophisticated and building codes have become more stringent, a thorough understanding of insulation application and the evaluation of its performance within the building envelope have become crucial to the long-term performance of all buildings. Three requirements in building design are addressed by the application of insulation or insulating materials within the building envelope assembly, and they are as follows. One, maintenance of temperature control within the building without using excess energy. Two, control of flame spread during the fire ratings of buildings components and assemblies. And three, the control of sound transmission. Because of their unique properties, insulating materials, when correctly selected, will resolve any combination of the three. So let's move to the next subsection of chapter 14, and that is thermal insulation. It is generally considered to be any material that has a relatively low coefficient of thermal conductivity. It impedes the transfer of heat from one phase to the other. Good thermal illustration is where a slab of cellular glass successfully retards the passage of heat through its thickness, for example. And you can see there are images here. You can see the thermal insulation. You see expanded polystyrene insulation. The Green Building Initiative, the USGBC or US Green Building Council is an organization promoting the benefits of sustainable construction. And it has developed a set of guidelines for environmental sustainable building construction and operation. LEED, or Leadership in Energy and Environmental Design, that is an international recognized set of measurable standards that can be used by building operators to evaluate the efficiency of existing buildings and by building designers to design energy efficient, environmentally friendly buildings. Energy efficiency, indoor environmental quality, and material selection relate directly to the construction of the building envelope. Choosing the appropriate materials for the construction of the building based on the local environment conditions contributes to a longer building life and minimizes the need for expensive retrofitting. The use of proper amounts of insulation reduces the amount of energy required to heat and cool the interior of the building. Proper air circulation and conditioning lessen the possibility of introducing harmful airborne organisms such as mold. Much is being done by organizations such as the U.S. Environmental Protection Agency, or EPA, and USGBC, or U.S. Green Building Council, in promoting new developments in building science. Insulation against temperature changes. And that is another use for thermal insulation to protect exposed structural sections from large temperature changes. Large fluctuations in temperature cause expansion and contraction of the exposed sections, which can cause unnecessary stresses in the building frame. Here you can see there are images showing rigid glass fiber bats attached with pins to concrete walls, and you can see how the pipes are insulated with cellular glass. And also you can see the air conditioning ducts lined with glass fiber insulation. Insulation of heat conveyors. Heat ducts and water lines are also covered with insulation to prevent heat loss. Rigid glass fiberboard is normally used to insulate heating ducts, whereas rigid insulation of cellular glass, glass fiber, and foamed plastics wrapped with metallic foil is used around pipelines. In some applications, heat ducts are lined with rigid insulation rather than placing the insulation on the outside. So when we talk about fireproofing, two material designations are recognized by fire codes when dealing with fire resistance rating of building assemblies: non-combustible and combustible. Non-combustible materials are mineral-based and include concrete, asbestos cement, gypsum plaster, glass, and natural rock, such as slate, sandstone, and marble. Combustible materials are those that contain or are formulated from animal or vegetable matter. Wood, fiberboard, paper, felt, plastics, asphalt, and pitch are typical examples. Construction materials that are a combination of combustible and non-combustible materials are usually considered combustible unless the quantity of combustible matter is quite small. The amount of fireproofing that is applied to a structural section depends on the fire resistant rating required and the type of material that is to be protected. Materials in general use for the protection of a structural steel frame, for example, include regular and lightweight insulating concrete, cellular concrete, gypsum wallboard, plaster, and sprayed-on mineral wool. Fire ratings. All modern building codes provide guidelines for minimum fire resistance ratings of building components. The initial criterion for establishing building component fire ratings is the anticipated occupancy or combination of occupancies for the building. During the initial design stages of a building, a major occupancy classification is assigned to the building in question, and from this point on, all design decisions are controlled by the given classification to ensure a safe and fire-resistant structure. Typical occupancy classifications include assembly, that's for A for assembly, and those are arena type and theater type occupancies, for example. Then I for institutional and their care and detention type occupancies, R for residential, B for business, and M for mercantile. Then other occupancies as well, and they range from low hazard to high hazard conditions. You can always refer back to the IBC or International Building Code to see all the occupancy classifications and the full description of those. So once the building size, location, and the occupancies are established, fire ratings for all structural components must be determined. These can vary from 1 to 3 hours or more, depending on the required fire separations. Every portion of the building assembly is evaluated according to its location and use in the building. Roof assemblies, floor assemblies, stairwells, partitions, exposed beams and columns, load-bearing walls, and exterior walls must all be evaluated on their ability to resist the effects of fire for a predetermined length of time. Research labs such as UL or Underwriters Laboratories Incorporated and government institutions conduct fire tests on building materials and various assemblies and provide design data such as flame spread ratings, smoke developed classifications, and fire ratings. So let's talk about methods of fireproofing. For example, there is a fireproofing method that is pertaining steel beams and columns, and that's fireproofing with concrete, and that can be achieved by encasing the members in cast-in-place concrete. This method involves building a form around the structural steel section or using a prefabricated form. When concrete floor slabs are used with the steel frame, fireproofing is usually cast as part of the slab. Here, please refer to the images. You can see fireproofing forms supported from below, as well as the fireproofing forms supported by hangers. You can see this section of that. Another section is fireproofing form supported by steel strapping. So that's another way of doing that. And you can see the section actually showing that. Columns are fireproofed with concrete by first building or fitting a form around them and then filling it with concrete. It is sometimes advantageous to build the form in two sections, upper and lower. Place and fill the bottom section first and then the top section. Here you can see another image showing fireproofing a girder with cellular concrete, as well as column fireproofed already with cellular concrete. Another way to do that is gypsum wallboard, and it's one of the most common materials that is used as a covering over framing members to provide fire protection. A 5/8 inch thick fire-rated wallboard can provide up to 1 hour fire rating when properly applied. And you can see there is a section showing that. So we are moving to the next subsection, and that is building insulation. The thermal efficiency of a building is based on the insulation values of the building systems that make up the protective blanket or outer skin of the building. Present-day designers must give careful consideration to the amount of insulation used in floors, roofs, and outer walls, and the impact of its location on the various components within the assemblies. The same attention to detail must be given to the application of insulation as is given to the structural analysis of the building frame or in the assignment of correct fire ratings to building components. Heat transfer occurs in three ways. We already know that. That's conduction, convection, and radiation. Conduction is the transfer of heat through a material. Metal and concrete, for example, are better conductors of heat than wood, making them less effective insulating materials compared to wood. Because wood is less dense than concrete or steel, it also has more air voids. It has better insulating properties than either steel or concrete. On the other hand, insulating materials such as expanded polystyrene or glass fiber bats have superior insulation values when compared to wood. Good insulating materials have a high percentage of air voids and physical properties that restrict the movement of air through them. Convection is the transfer of heat through the movement of air. Cold air is denser than warm air, and air rises when heated. This movement of air makes the room feel cooler than it really is. Air movement such as this will occur within the cavity of a wall system that is not properly sealed and results in heat loss that can also contribute to moisture problems within the cavity wall, the wall cavity, excuse me. Radiation is the transfer of heat energy by absorption. Darker materials absorb more energy than lighter materials. A shiny surface will reflect more energy than it absorbs. This concept can be used to contain heat energy within a contained space, or it can be used to reflect unwanted heat energy. Thermal conductivity is defined as that property that determines the quantity of heat that will flow through a unit of area of a material based on the temperature difference of 1 degree Fahrenheit. Units for thermal conductivity are BTU inches and in metric system, that's our square, our square meters, and Celsius for the temperature instead of Fahrenheit for the imperial system. The thermal conductance C or of material is defined as the amount of heat in watts transmitted through a thickness of material or a combination of materials over a unit area, producing a temperature difference of 1 degree Fahrenheit, and is calculated by dividing the thermal conductivity by the material thickness. The resulting units become BTU per hour square feet in Fahrenheit, temperature in Fahrenheit. The lesser heat a material allows to pass, the better the insulating quality of the material. The resistance to heat flow through a material, or R factor, is the inverse of the conductance. So it's 1 divided by C. Each material has its own particular R value. The greater the R factor, the better the insulating qualities of the material. Here, please refer to the chart. You can see typical material thermal resistance factors. Nothing to memorize, but you can just use it to compare, for example, the R factor of rigid glass fiber is 4.4, and the R factor of, for example, stucco is 0.15, so you can see the difference. The heat transmission coefficient, or the U factor, is defined as the amount of heat in BTU transmitted through 1 square foot of a building section, whether it's roof, wall, or floor system, in 1 hour for each degree Fahrenheit. Or temperature difference between air on the cold side and air on the warm side. And again, here is a problem with the solution. So please take a look at that. A well-constructed and well-insulated wall will ensure that the dew point temperature occurs at a point in the wall section where the resultant moisture can be eliminated. The best scenario is to have the wall constructed in such a fashion so that the dew point is never reached. However, this may not be practical. The use of an appropriate arrangement of insulation, air vapor diffusion retarder, and air barrier, along with the use of mechanical equipment to control humidity levels and air pressures, is the current approach to obtain an optimal thermal efficiency within the building. Though through hard experience, it has become evident that the wide brush approach to building envelope design is no longer adequate. Experts in the field of building science, such as the Building Science Corporation, for example, through on-site testing and evaluation, have developed strategies for workable building envelopes based on various climate conditions, materials, and construction techniques. An important requirement of a well-constructed building wall is to minimize warm, moist air from entering the wall, cooling and condensing, and potentially causing damage to the wall components. The temperature at which condensation occurs is known as the dew point. The dew point can be defined as the temperature at which air having a certain relative humidity will condense when cooled. Good building envelope design dictates that any moisture entering a wall cavity must be allowed to escape by drying or by drainage. The ideal situation is to keep the wall cavity perfectly dry. However, we know that in reality, this is usually difficult to achieve. So please refer to the image here. You can see this section and it shows the temperature gradients in insulated walls. Also, that shows the difference of temperatures between the inside and outside. So insulation application. There can be a perimeter insulation, and buildings constructed on surface foundations are subject to perimeter heat loss and footing movements. Perimeter insulation helps control this heat loss and protects the footing from frost action. Here you can see there are images showing shallow footings protected against frost action. You can see the difference between heated building and unheated building, how that is done. So also you can see perimeter insulation outside, how that works. So the insulation around the perimeter of a building may be placed on the inside or the outside face of the foundation. When applied to the outside, the portion above grade must be protected from physical damage with a covering of treated wood, stucco, or metal lath, or asbestos cement board. When slab-on-grade construction is involved, the perimeter insulation should be installed prior to backfilling of the foundation trench. The insulation should be carried down to the frost line or down the top of the footing. The type of venting and the amount of venting will depend on building conditions such as heating requirements and insulation of the floor assembly. If the floor slab is to contain heating or air conditioning ducts, insulation should be placed under them to minimize heat loss. Rigid insulation can also be used under the remainder of the slab to further reduce heat loss. Please refer to the images here. You can see the perimeter insulation with slab on grade, as well as the perimeter insulation in the crawl space. Also, you can see the perimeter insulation with slab ducts, and also image showing foam plastic rigid insulation on foundation wall. And that is number 2, foundation wall insulation. Foundation walls are usually insulated with some type of rigid insulation, including insulating boards and rigid slabs or blocks. Insulating boards include wood and cane fiber boards, straw board, and laminated fiber boards. And again, there is an image and the section showing insulation held by wire clips. So rigid slab insulations are applied to the wall surface with hot asphalt, Portland cement mortar, special synthetic adhesives, or wire clips. Walls must be clean and smooth before insulation is applied to ensure a good bond. It may be necessary to backplaster the wall to achieve the necessary finish. And you can see foundation wall strapped for insulation. And also there is an image showing expanded polystyrene block units used in foundation application. And that's another method of creating insulated foundation walls, the use of expanded polystyrene block units. So these units are stacked much the same way as masonry units and filled with concrete. Horizontal reinforcing bars are placed at intervals up the height of the wall and they add strength to the wall. The block units must be supported with temporary bracing to prevent misalignment during the concrete pour. So you can see there is an image showing that. And we're moving to number 3, that is curtain wall insulation. Masonry curtain walls may be insulated similarly to the methods applicable to foundation walls. Brick or block curtain walls are often built as cavity walls. However, insulation should not be placed within the cavity as this is an area of moisture control. Insulation should be kept dry and thus should be placed in a protected section of the wall, such as loose fill within unfilled masonry cells or by placement of rigid or batt insulation on the interior of the wall. Ceiling insulation. Let's talk about that a little bit. So insulation may be applied directly to the underside of floors or a suspended sealant system may be employed. In either case, many kinds of insulation may be used, including insulating boards, rigid slabs, or sprayed-on insulation consisting of vermiculite plaster or cellulose. Please take a look at the image showing insulation on solid ceiling. And you can see also the suspended T-bar ceiling. You can also find the suspended metal pan ceiling and suspended ceiling frame, as well as the sprayed-on insulation on concrete ceiling. Number 5, roof insulation. Roof decks may be insulated with any type of rigid insulation, including cellular glass, rigid foam plastic, straw board, fiber boards, and cellular concrete. With concrete, gypsum, precast slab, or steel decks, no undercoating is normally required, but sheathing paper or roofing felt is nailed over a wood deck. And again, please refer to the images. You can see insulation application to roof deck. And you can see concrete deck, wood deck, and steel deck. When we talk about the use of reflective insulation, that may be produced from any metallic substance that has the ability to reflect infrared rays. Aluminum foil has proved to be the most practical and economical material for this purpose. It is produced in several forms, including foil-backed gypsum lath, rigid insulation with foil back, foil laminated to craft paper, corrugated paper with foil on both sides, and plain sheet foil in rolls. So again, refer to the images, please. We are moving to the sound insulation and control. And also we will have one more section, and that is moisture control. So let's talk about sound insulation. There are two main problem areas concerning sound and its control in old and new buildings. One is the improvement of hearing conditions and the reduction of unwanted noise in any given room. And the other is the control of sound transmission from one room to another room through walls, floors, and ceilings. Sound waves travel through the air in the form of small pressure changes, alternatively above and below the normal atmospheric pressure. The average vibration and pressure above and below the normal is called sound pressure, which is related to the loudness of a sound. A sound wave is one complete cycle of pressure variation. And you can see there is an illustration showing that. So the control of reverberations is accomplished by the use of products that have a much greater ability to absorb sound waves than most building materials. The amount of sound absorbed is measured in sabins, one sabin being equal to the sound absorption of 1 square foot of perfectly absorptive surface. The fraction of sound energy absorbed at a specific frequency during each reflection is called the sound absorption coefficient of that surface. Some surfaces are primarily reflective, such as glass, concrete, or masonry, absorbing perhaps 5% or less of the sound energy. Such materials have sound absorption coefficients of 0.05 or less. On the other hand, some acoustical materials can absorb 90% of the sound energy and have a coefficient of 0.9 or better. Uh, so most sounds contain a range of frequencies. It is necessary to use an average of the absorption coefficients when considering sound absorption. A means of comparing reducing for noise that is mainly in the middle frequencies has been developed. It is called the noise reduction coefficient, or NRC, and represents the average amount of sound energy absorbed over a range of frequencies between 250 and 2000 hertz. The exact amount of sound absorption required for various rooms is difficult to state because of individual differences in noise interpretation, but 3 general guidelines may be used. In larger rooms with low ceilings and widely spaced medium density noise sources, such as general offices, a minimum average absorption coefficient after acoustical treatment of all surfaces should be 0.2. In smaller rooms containing closely spaced or high-level noise sources such as business machines, the maximum average absorption coefficient after treatment should be 0.5. To create a definite, noticeable improvement in noise reduction, the average absorption coefficient before treatment or the total room absorption should be increased at least 3 times. However, the application of this rule is subject to minimum and maximum values of the first 2 rules. Please refer to the images, and also there is the ceiling layout for tile application. And this brings us to discuss the sound absorbing materials. So those materials are called acoustic materials and can generally be classified in 3 groups: acoustic tiles, assembled acoustic units, and sprayed-on acoustic materials. Acoustic tile is intended primarily for ceilings, but may be used on upper wall surfaces as well. When used over a solid surface such as plaster, plywood, or hardboard, the surface must be smooth, even, and clean. Tiles may be secured with nails or adhesive, depending on the type of backing used. In any case, the 2 center lines of the ceiling should be drawn first, and tiling should begin at the intersection of these lines. And you can see there is an image showing that, as well as the acoustic ceiling tile on furring and acoustical tile in a suspended ceiling with the T-bar support and the H-bar support. Vermiculate plaster is a ready mixed product requiring only the addition of water. It can be applied over any firm, clean surface such as plaster base coats, masonry, and galvanized metal. It is applied in 2 coats, no more than ½ inch is required, or 3 coats of greater thickness is specified. So let's move to the sound transmission control. Nearly in all types of construction, sound transmission from one room to another takes place as a result of diaphragmatic vibration through walls, floors, or ceilings. The vibrations may be initiated by impact, such as a footstep, or by the action of sound waves striking the surface. One vibration is known as impact noise transmission and the other as airborne sound transmission. Standard lab tests used to evaluate wall assemblies for airborne sound transmission and floor assemblies for impact noise transmission are ASTM E90 and E492 respectively. Impact transmission normally takes place through floors and ceilings, and there are several ways of reducing it. One is to cover the floor with a resilient material such as cork, tile, or heavy carpet to absorb the impact. Another is to use a suspended ceiling between floors. This is particularly effective if resilient hangers are used. Good results are also obtained by using a floating floor. This floor may be a separate 2-inch concrete slab isolated from the structural slab by a 1-inch foamed plastic or paper-covered fiberglass kilt. It may be a wood floor nailed to steepers that are supported on the flat steel springs. And you can see there are images showing that. The sound insulating efficiency of a wall or floor assembly is designated as its transmission loss, and it's measured in decibels. Based on this loss and using standard methods of calculation such as those outlined in ASTM E413, each assembly can be assigned a sound transmission class or STC. Typical STC rating values for floors and partition wall assemblies range from 35 to 70. An STC rating value of 50 is considered to be a minimum acceptable value for most building applications. The impact insulation classification, or IIC, of a floor to ceiling assembly may be tested in the field using ASTM E1007. 7 different sound transmission field test methods may be used for determining sound transmission through partitions and exterior walls, depending on the application. There are several types of wall assemblies that can achieve STC ratings of 50 or better. And for example, a single width masonry wall having a mass of 80 PSF, 8-inch or of brick, or 7-inch of concrete, including plaster. Then it can be a composite wall consisting of basic masonry wall having a mass of at least 22 PSF. And there are a few examples showing that, a few diagrams, please refer to them. Wall construction that will provide STC ratings from 45 to 49 include the following. That's a single width masonry wall, a composite wall that similar to the one we discussed above, and a staggered wall, stud wall with a drywall. So please refer to the images here. And floors that will have an STC rating of 50 and above will include the following: a 4-inch solid concrete slab having a mass of at least 50 PSF, plastered directly on the underside and covered with wood flooring on wood fern strips. Also, an open web steel joist framework covered by a paper-backed fiberglass or foamed plastic kilt supporting a 2-inch concrete topping. So let's move to the last subsection, and that is moisture control. The prevention and control of moisture penetration in the building assemblies remain constant challenges to building designers and builders. Moisture may migrate through building envelope assemblies in either a liquid or a vapor form. As a liquid, moisture penetration is usually from the exterior to the interior. However, in case of water vapor, it can move in either direction depending on the relative conditions between interior and exterior. Mold. So with changing climate conditions and the increased sophistication of building technology, new problems have evolved that in the past were not a serious concern. The growth of mold in building assemblies is one such problem. Although mold exists in nature and grows in the natural environment, certain types of mold can be harmful when they occur in a building, especially where the residents may have some type of immune deficiency. Hospitals and long-term care facilities are good examples where mold can become a serious health risk. So molds are very simple organisms and require three basic needs to grow and multiply: a place to grow, moisture, and nutrients. And we know that most materials will support mold growth if there is a sufficient moisture. So the best way to control mold growth is to control moisture. Moisture control in building envelopes. With water vapor that moves through building an ensemble in two ways, one by vapor diffusion and the second one by air movement. So water vapor diffusion can be defined as the passage of water in vapor from through a material. The best approach to control the water diffusion through wall assemblies is the use of air vapor diffusion retarder. These are materials that have low permeability and minimize the diffusion process. Materials commonly used as vapor diffusion retarders include polyethylene film, spun-bonded polyolefin materials, wax, craft paper, foils of aluminum or other metals, and latex paint. So in many applications, the air vapor diffusion barrier doubles as the air barrier to control both infiltration and exfiltration. To be effective as an air barrier, the vapor retarder must have sufficient strength to withstand air pressure deficiencies due to mechanical system and pressure due to wind. To control an air infiltration, air barriers, commonly known as building wraps, are applied under the exterior finish or siding. And here you can see there is a section showing insulated wall section for cold climates, and the air vapor retardant is diluted or moved to the exterior for warm climates. Please remember that. Masonry and concrete walls below grade are damp-proofed by the application of various formulations of fluid-applied membranes, either asphalt-based or polymer-based, with a coating of cutback asphalt, with the Pargin or asphalt mastic, or with the cement-based polymer-modified coating. Concrete slabs on ground may or may not need an air vapor diffusion retarder depending on their end use. Also, let's talk about sealants and adhesives. As building codes and standards become more stringent, the need for high-quality, environmental safe sealers and adhesives has never been greater with the construction industry. Chemical companies have developed a wide variety of compounds that are virtually unaffected by sunlight, moisture, and temperature changes. And the various formulations exist in either liquid that can be poured or as a caulking for gun application. Typical applications include saw cuts in concrete floors for control joints, precast concrete panel joints, exterior insulation and finish systems, curtain wall joints, mullion joints, and glazing. The effective sealing around mechanical piping and ducting passing through fire-rated walls, floors, roofs, and building envelope membranes is achieved by using special formulations that will retard flame spread during the fire. In modern building design and the retrofitting of existing buildings, the application of these sealants has evolved as a separate trade. In general, all sealants and adhesives require some preparation of the substrate materials to ensure proper bonding. Joints must be free of deleterious materials such as concrete formwork release agents, surface dirt or dust, all surface treatments, and any other substances that may inhibit proper adhesion. Excuse me. And elements to consider when specifying a particular sealant are as follows. The type of substrate, the amount of movement at the joint, exposure conditions and thermal ranges, joint loading conditions, required curing, tooling, and tag-free times, color of the finished joint. And this wraps up our chapter 14. Thank you so much for watching. I will see you in chapter 15.